Okay, these are the class highlights for Chapter 9, which is Unit 6 in this class. And this is all going to be about confidence intervals and hypothesis tests involving two different population parameters, either two proportions or two means. So in each case, we'll have two different samples that we're talking about. First, we're going to talk about making inferences about two population proportions. So in this section, section 9.2, we're going to test a claim made about the difference between two population proportions. We're also going to talk about constructing a confidence interval estimate of the difference between two population proportions. So here's some notation that we need to do either one of those two things. Since we're going to be talking about two different populations and two different samples, we actually have two different sets of notation. So this first set that's shown here all comes from whatever we decide is our first sample. So we have our population proportion that goes with the first population. We have our sample size for our first sample, number of successes in our first sample, and then we have our sample proportion for the first sample, and then Q is always 1 minus P no matter what we're talking about. Then for population 2, it's going to work the same way, except that all the subscripts will be 2's instead of 1's. Now this is another formula that we'll need specifically to do the hypothesis testing. This is called a pooled sample proportion. What this means is that we're taking all of the sample data and pooling it, so we're treating it like it's all one big sample. So we'll take the number of successes from the two samples and add those together. We'll take the two sample sizes and add those together, and then we'll create a proportion out of those two things. So that's our pooled sample proportion. And we'll also have to have a Q that goes with that, so that will be 1 minus this proportion. The requirements, if we're looking at two proportions, are that our samples have to be independent, so they can't have a relationship to each other, and they both have to be simple random samples. And for each of the two samples, the number of successes has to be at least 5, and the number of failures has to be at least 5. Here's an example. Here we have some data about fatalities in car crashes, depending on whether there was an airbag available or not. So we're going to treat these as two different samples. The ones where the airbag was available will be our sample number 1. Where there was no airbag available, that will be our sample number 2. We're going to start out by comparing these two. So if we're considering the airbag available population 1, then our N1 would be the 11,541, the sample size there. Our sample proportion for that first sample would be the 41 over the 11,541, because what we're interested in, what we're considering a success in this particular case, is a fatality. So our number of successes is 41, and then we're dividing by the sample size. And that would mean our Q1 with the hat would be 1 minus that. So we could write it as a fraction here as 11,540 over 11,541. And in both of these cases, we could convert these values to decimals. And for population 2, we're just taking the numbers from the second column over here where there was no airbag available. So we have 52 for our number of successes, 9,853 is our sample size. Here's our sample proportion and the complement of that. And our pooled sample proportion, as I said, we'll need this if we're going to conduct a hypothesis test. We just take the number of successes in each one and add those together. And for the numerator of this, we take our two sample sizes and add them together. Okay, if we're actually going to construct a confidence interval estimate of the difference between the two proportions, then just like when we did confidence intervals before, we're going to start out with a point estimate. And our point estimate is going to be the difference between the two sample proportions. So it's actually going to be the P1 with the hat minus the P2 with the hat. So we'll do the same thing we did before with confidence intervals. We start with that point estimate, we figure out our margin of error, and here's the formula down here, and then we take our point estimate and we subtract the margin of error to get our lower confidence interval estimate, we add the margin of error to get our upper confidence interval estimate. So let's try this. We're going to construct a 90% confidence interval estimate of the difference between our two population proportions for the airbags problem. Okay, so our requirements are satisfied. We had 2 independent samples and we have at least 5 successes and 5 failures for each one. Now for our point estimate, again, that's our P1 hat minus our P2 hat. And our P1 hat, remember, was the 41 over 11,541. Our P2 hat was 52 over 9,853. If we calculate some decimal values here, then for the 41 over 11,541, I'm taking this out to 6 decimal places just so that we make sure that we have enough. So there's our first decimal value, and then our second one is there. So if we subtract these two, we have a negative value for the difference between our two sample proportions. And notice that here we can end up with the negative value because we're talking about the difference between the two sample proportions. What this tells us in general is that the first sample proportion was smaller than the second sample proportion. That's why we got a negative value when we subtracted them. Okay, then we need our critical value if we're going to construct a 90% confidence interval. So remember, for confidence intervals, we take the alpha, which is going to be 0.10, and we divide that in half. And then we're going to either find the closest value to this in our table, or on your calculator, you can use the inverse norm function. Okay, which is going to give you on your calculator a negative 1.645 if you round it to 3 decimal places. And remember, with this, we just take off the negative, so we've got our critical value being 1.645. All right, now our margin of error, we have this long formula. So if we put in all of the values that we have into this formula, we have our critical value here, and we have our two sample proportions here, and we have the Q values. And notice in each one we have to put the correct sample size underneath. It's really important here that you use the correct order of operations in order to get the correct answer. If we go through all this, we'll come out with a margin of error of 0.001507. Now to construct our confidence interval, we just have to take our point estimate and subtract our margin of error and add our margin of error. So our point estimate we had was, there's our point estimate, and we're going to subtract our margin of error. And subtracting those two, which is going to give us a negative 0.003232. And over here we're taking our point estimate and adding our margin of error. And remember, in both of these our point estimate is still negative. Okay, and if you're doing this on your calculator, or at least on mine, it gives me an answer that looks like this. Remember, this is scientific notation. That actually means that we have negative 2.18 times 10 to the negative 4th, which is the same as negative 0.000218. Okay, so we have our two limits for our confidence interval. So our confidence interval looks like this. Now, if you notice, both of our limits are negative. They don't include 0, which means that 0 is probably not a possibility for the difference between these two population proportions. Since they're both negative, that means in general that our first proportion, the P1, is smaller than the second proportion, because that's what they'd have to be for this to come out negative. So another way of saying this is that we do see a significant difference between the two proportions. And again, if we go back to what the problem was, that tells us in general that the fatality rate is lower for people in cars with airbags than for people in the cars without the airbags. Okay, now we're going to go on to hypothesis testing if we have two proportions. So for this one, you don't have to think too much about what the null hypothesis is. It will always be the same thing, and that is that P1 is equal to P2. For your alternative hypothesis, again, you're going to have the P1 and the P2. The only question is what the inequality is going to be. So it'll either be a not equal to, a less than, or a greater than, depending on what the claim is. And we're going to assume, again, since in our null hypothesis we have P1 equal to P2, then we're assuming that P1 minus P2 is equal to 0. So right here in this formula for your test statistic, this part of it right here is automatically going to be 0. All right, and when we're testing these claims, we can either use the p-value method or the critical value method. So let's go through with the same sample data that we had before and test the claim that the fatality rate of occupants is lower for those in cars equipped with airbags than those in cars that didn't have airbags available. Okay, so we already talked a little bit about the requirements for this. They're the same as they were for confidence intervals. So we already know those are satisfied. For our hypotheses, again, we're making this sample 1, just so that we keep this straight, and this one is sample 2. So our null hypothesis, remember these are always going to be the same. So we've got that our two population proportions are the same. And one thing you also need to know, if you're using StatCrunch or some other software to do this, a lot of times we go ahead and subtract our P2 from each side. So our null hypothesis can also look like this. That gives you, you'll see when you're using StatCrunch on your tech assignment, that they do ask you what this number is here. Is always going to be 0 when we're talking about two samples. Okay, so that's our null hypothesis. That one's easy. Now for our alternative hypothesis, again, if our fatality rate for our first population is lower than for our second population, that means that if we compare the two, we would want to put a less than in between those two. So this would be a less than, and again, we could also write this by subtracting the P2 from each side. We could also write this way. So we could make it P1 minus P2 is less than 0. All right, they told us in the problem that they wanted us to use a significance level of 0.05. And here's where we need that pooled estimate that we were talking about to use in our test statistic formula. Again, we're adding our two numbers of successes on the top, we're adding our two sample sizes on the bottom, and this is our pooled estimate. And the Q with the bar is just 1 minus the P bar. Here's our whole test statistic formula. And again, this part right here we don't have to worry about because it's 0. All these other numbers we can put in here. Here's our 0. And if you go through and calculate this, we get a test statistic of negative 1.91. Now for using the p-value method, remember that means that we put our test statistic on our distribution picture, and since our alternative hypothesis had a less than, that means we have a left-tailed test. So we're going from here to the left and seeing what that probability is, or what the area is. If you look this up in the table, if you just look up negative 1.91, you're going to get 0.0281. If you want to do this on your calculator again, then you would do normal CDF. We'd have to put in a lower bound of, say, negative 10 here. And then our test statistic, and then 0 and 1. All right, either way, we've come out with a p-value of approximately 0.0281. So for our initial conclusion, Remember, we're comparing our p-value and our alpha. Here's our p-value, here's our alpha. The p-value turns out to be less than alpha. That tells us that our conclusion is to reject the null hypothesis. If the p-value is less than alpha, then we reject the null hypothesis. So that says there is sufficient evidence to support the claim that the proportion of accident fatalities is less for those with airbags than for those without airbags. So remember, anytime that we reject, then that says that there is sufficient evidence. Okay, now let's go on and talk about comparing two means. And we're going to have two different situations for this. One is where we have two independent samples. The other is where we have what we call dependent samples. So first we'll talk about the independent samples. So this is where we've got just two different samples. Populations aren't related to each other. And we can either test a claim about the difference between the two means, or we can construct a confidence interval estimate. Okay, so again, when we're talking about independent, that means that the members of one population aren't paired or matched with the other population. The other situation we can have is where we're picking something like a before and after, or as you'll see in your tech assignment, where we have mothers and daughters that are picked together. So something like that would be a matched pair, and that would be a dependent sample. But for our independent sample situation, then again we've got our two populations and our two samples. So we've got two sets of notation. Our mu1 is our population mean for our first sample, and this would be our population standard deviation for our first sample, although we're not really using that. Sample size for the first sample is n1. x1 bar is our sample mean for our first sample, and s1 is our sample standard deviation for our first sample. And these are all the same for the second sample and population, only they have 2's instead of 1's. And the only case that we're doing here is where we're assuming that our population standard deviations are unknown, and we don't know anything about our population standard deviations. We've got independent samples, both are simple random samples, and for both samples, either the populations come from normal distributions or both sample sizes are greater than 30. And here's our test statistic formula. And again, in this case, we're going to assume that we're going to have our two means equal for our null hypothesis. So this part of this formula is going to be 0. That just makes things a little bit easier. Okay, and since we're using the t-distribution for these, we will need to know about degrees of freedom. You'll see when you use StatCrunch that they actually calculate the degrees of freedom. There's a formula that they use to do that. If you're doing homework from the book, here's a much simpler way that they use in the book and that you can use to do your homework. Just look at the two sample sizes, take the smaller of the two, and find your degrees of freedom from that. So figure out what n1 minus 1 is and n2 minus 1, and just use the smaller of those two numbers for your degrees of freedom. All right, and if we're looking at confidence interval estimates, then again, if we're looking at the difference between our two sample means, this is going to be our point estimate. We're going to subtract the margin of error and add the margin of error, and here's our margin of error formula. And again here, we're going to be using, when we do this by hand, we're going to be using the smaller of n1 minus 1 or n2 minus 1 for our degrees of freedom. Here's an example. We're going to start out by testing the claim here that men and women speak the same mean number of words in a day. So we've already got our sample data all laid out for us. And notice here that men are the first sample and women are the second sample. And we're assuming we don't know the population standard deviations, that we have two independent samples, that they're both simple random samples, and both samples are large enough by far to satisfy the greater than 30 requirement. Okay, so for our hypotheses, again for these, the only kind of problems we're going to do here are where the two means are equal in our null hypothesis. And again, we can write this, we can write this as subtracting the mu2 from both sides so that we have mu1 minus mu2 is equal to 0. Now for our alternative hypothesis, the claim was actually that these two are equal. So the opposite of that is that they would be different. And that means we're going to have a not equal to. So again, we can write this in two different forms. We can write this as mu1 minus mu2 is not equal to 0. We know our significance level is 0.05 again. And again, this part of the formula is 0. So here we're just putting in our sample data that we were given. So we've got our sample means here, our sample standard deviations here, and you do have to square these. And then we have our two sample sizes here. This gives us a test statistic of negative 0.676. Now, since this is with the t-distribution, we're going to use the traditional method with the critical values. So here we had a not equal to in our alternative hypothesis, which means that we have a two-tailed test. And if we look at our two sample sizes, the smaller of the two was 186. So we're using 185 for our degrees of freedom. Since that's not in our table, the closest one we can come up with is, it's probably where degrees of freedom is 200. So we get t is equal to 1.972. Now since this is a two-tailed test, we're using that one and the negative value also. So we have our two tails, and so these are our two rejection regions or critical regions. Now if we plot our test statistic would be somewhere over here. It's fairly close to 0. So it's definitely not in either of those two shaded regions. So it's not in our rejection regions. And that means that our initial conclusion here is that we fail to reject our null hypothesis. Now this one, our final conclusion, is worded a little differently because of what the claim was. The claim was that men and women do speak the same mean number of words in a day. So that the claim was actually that the means are equal. So the question is whether we've got enough evidence to reject that claim or not, and we don't. And again, anytime that we're failing to reject the null hypothesis, the fail and the not go together. So the fail is going to say we don't have sufficient evidence. Okay, now we're going to use the same data and construct a confidence interval for the difference between the means. So we have all of our sample data. We actually already found our critical value when we were doing our hypothesis test, so that's 1.972. We're putting all of our sample statistics in here, and we get a margin of error of 1,595.4. And we've got our two sample means, so to get our point estimate, we're going to subtract those two. So we've got our point estimate right here. We're taking that and subtracting our margin of error, and then we're taking that point estimate and adding a margin of error, and here's the final answer that we would get for our confidence interval. Now notice that one of these is negative and one of these is positive, which says that our confidence interval includes 0. And that means that it's entirely possible that the two means are equal. So in that case, we would say that it doesn't appear that there's a significant difference between the two population means. Okay, now we're going to look at the case where we have dependent samples, or as we call them, matched pairs. So in this case, there's some relationship between the values in the sample. So if we look at one observation, we've got, so if we look at one row of the data, there's a relationship between the two values that are in that row. So what we're really looking at here is the differences between the values for each matched pair. So one thing we could do is calculate all those differences, and then we would look at the mean of those differences. So here's really the value that we're looking for for each different pair is the difference between the values. Then we're finding the mean of that. So we're finding the mean of all those differences. And this, again, since it has the mu, this is for the population. This is for the sample. So again, this is the mean of the differences for the sample. This is the standard deviation of the differences for the sample. And n is the sample size, so it's the number of pairs of data that we have. So the requirements here are that the sample data have to be dependent, and that we have simple random samples, and either we had a normally distributed population in the first place, or that we've got at least 30 for our sample size. Here's our test statistic. It's not quite as complicated as it was for the other two that we looked at. So again, this is our sample mean for the differences. This is our population mean. This is our sample standard deviation for the differences, and this is our sample size. Degrees of freedom here, since we're using the t-distribution, we're just using n-1. And if we're doing confidence intervals, then the d bar is our point estimate, since that comes from our sample. So we're taking that, figuring our margin of error, and subtracting it and adding it. Here's an example. This one, they took some college freshmen and weighed them in September and then again in April. That gives us matched pairs because the two weights came from the same person, just at different times. So each of these pairs is related to each other by coming from the same person. So here we would calculate our differences. This is going to be the April minus the September weight for each one of these. So there are differences, and so we're going to calculate statistics from these differences. We need our mean, which is d bar, and our sample standard deviation, which is the s with the d. And then our sample size here is only going to be 5. Okay, so if we're testing the claim that the weights are different, that means that our difference is going to be different than 0. So for our null hypothesis, we're going to say that the difference is equal to 0. For our alternative hypothesis, since we're just saying that the weights are different, we're going to just say that d is not equal to 0. Our significance level was 0.05. And here were our 5 differences that we had. If we calculate our statistics from that, if we calculate the mean of these differences, it's 0.2, and the standard deviation for these 5 values would be 2.4. So we can plug everything in here. Remember, again, this value right here is going to be 0 because this came from our null hypothesis. And if we plug in everything else, we get a test statistic of 0.186. Now if we look up, since this is a two-tailed test, because we had H1 being that D was not equal to 0, so that gives us a two-tailed test. So if we look up in our table, we're going to have 4 degrees of freedom, and if we look under area in two tails, under 0.05, then we get a critical value of 2.776. So we use the plus and the minus for our two tails. So here's what our picture looks like. We've got our 2 critical values, our 2 tails with our 2 rejection regions, and again our test statistic is in here. So it's definitely not in either of those 2 rejection regions. So our initial conclusion would be that we fail to reject the null hypothesis. And remember, that fail automatically tells you for your final conclusion that we're going to be saying there's not sufficient evidence. So we're saying that there's not sufficient evidence to support the claim that the mean change in the weight is different than 0. In other words, there's not a significant weight change from September to April. Now we could also, using StatCrunch, we could use the p-value method. And if we did that, we'd find that there would be a p-value of approximately 0.8605. This is a very large p-value. Remember, if the p-value is large, that means that we fail to reject. Now, to do a confidence interval for this, again, we want to find our point estimate, which is going to be the sample mean for our differences. So that's the 0.2. We've got our sample standard deviation, our sample size, and we already found our critical value. So here's our formula for our margin of error. Oops, and this got a little messed up here. There should be an equal sign in there. And if we calculate that out, we get a margin of error of 3.0. So again, we're taking our point estimate minus our margin of error, and then over here our point estimate plus our margin of error, and here's the confidence interval that we end up with. And again, notice since the lower limit is negative and the upper limit is positive, that means that 0 is included in this interval. And that means that the mean of the differences could actually be 0, which tells us that there's not a significant difference between the weights.